Welcome to Let's Get to the Marks, going through some questions on A-level chemistry, hydrated salts. Let's go. All these questions just go on and on and on. When hydrated strontium chloride is heated, the water of crystallization is removed, leaving a residue of anhydrous strontium chloride. Scrolling down, a student carries out an experiment to find the value of X in the formula of hydrated strontium chloride, SrCl2.xH2O. The student's method is outlined below. Step 1, weigh an empty crucible. Add strontium chloride hydrated to the crucible and reweigh. Heat the crucible and contents for 10 minutes and allow to cool and reweigh. Heat the crucible residual for another 5 minutes, allow to cool, weigh the crucible and residue. Repeat step 3 a further 2 times. Right, so in total, they've heated it and weighed it 4 times. Why are they doing that? The student's results are shown below. Mass of the empty crucible, 15.96. Mass of crucible and the strontium hydrated strontium chloride is 18.65. First mass of crucible plus residue, 17.66. Second mass, 17.61. Then it goes to 17.58 and 17.58. So they've heated until a constant mass, which you always do with these hydration calculations. Calculate the value of X in SrCl2.xH2O. Give your answer to 2 sig fig, and it's worth 3 marks. A lot of work to get on here. We're going to smash on with it. Let's go. Don't forget, grab your scientific calculator, pause the video, have a go, and then unpause and watch the explanation. So what we got going on here, first, let's work out how much hydrated strontium chloride we had. So hydrated strontium chloride is equal to total mass minus mass of empty crucible. So what the hell do I mean by that? Basically, I want to take 18.65, which was the mass of the stuff in the dish, 18.65, and I want to take away 15.96, and that is going to give me, let's not make too many mistakes here, Tom, 18.65 take away 15.96, that's going to give me 2.69 grams. You might say, what have I just worked out? I've just worked out this here, which is SrCl2.xH2O. That's the mass of that. Now, the second thing I want to work out, I need to work out my mass of this. So I'm going to go to here where it was heated till a constant weight. What has come off of this? When you heat it and it doesn't go down anymore, it means that all of the H2O is gone. So I can work out the mass of SrCl2 by doing, he finally gets it right, it's 17.58. And we're going to take away the empty crucible mass from that, 15.96. Oh my gosh, it's all falling apart today. 15.96. And what does that give us? So let's do it. 17.58, take away 15.96. At last, we get 1.62 grams. That's how much dried salt there is. That's how much hydrated salt there is. So now look what I can do between these two. I can work out how much water evaporated. Because look, that is the strontium chloride with the water. That is the strontium chloride without the water. So how much water is there? Let's do H2O is equal to 2.69, take away 1.62, and that is going to give me 1.07. 1.07 G is H2O. Okay, so now I know I've got 1.07 G of H2O. Let's work out my moles of salt, dry salt, my moles of water, compare the two, and the ratio, simplest ratio between them is going to be X. So my moles of strontium chloride, I'm going to need to get the old mass thing out, aren't I? M over MR times moles. Oh my good gosh. And now I need to work out the MR of that. Oh dear, dear, oh dear, oh dear. Let's go to the old periodic table. Strontium is 87.6. Chlorine is 35.5. So let's smash that all together and work out what we got. Huh? Where did my working go? Oh my good gosh, I lost all my working. I've just had to quickly type it all out again so you guys can see. So where were we? Right, let's work out our mass of anhydrous strontium chloride. So we want to do 1.62. We're going to do that over the mass of strontium chloride, which is 87.6 for the strontium, plus 35.5. Of course, that needs to be multiplied by 2. So essentially, we're doing What is it? 71 plus 87.6 equals 158.6, I believe. So let's do that. 1.62 divided by 158.6. That equals, I have a mass that equals, sorry, moles, not mass, we're working out moles. G over MR. So that equals zero point 0.0. I've got 102. Best to keep this in your calculator because it's just a fat number, right? 102.14, whatever. That's my moles of strontium chloride. Now I need my moles of water. Thankfully, I don't need to go to the periodic table for that. Hydrogen's 1 and oxygen is 16. So two hydrogens, two ones, 116 equals 18. So water has an MR of 18. You'll probably know that off by heart after a while, and you won't even have to look that up. So 1.07 divided by 18, and that gives us, what is it? 1.07 divided by 18 grams gives me 0.059, and it's like four recurring, four, right? So which is bigger? Well, you can look roughly 0.05 compared to 0.01. I've kind of got 5 times more water. So let's divide them both by the smallest and find out when we ratio it what we get. If we divide them both by the smallest, this is going to become 1. So I'm going to divide that by 0.0102, etc. And that is going to be 1. And the ratio is going to be that divided by 0.010214, and I get I got like 5.81. Oh gosh, I don't know. I've not kept everything in my calculator. So that's 3 significant figures. At A level, we normally go to 3, but that is only 2. So you're not going to get the marks for what I've done there. You need to bash off one of those and just go down to 2 significant figures like that. And there you can see that is our answer. That is what X equals, peoples. This is a request from Abigail Thomas, so one of the viewers. So we're going through AQA A-Level Chemistry, Paper 1, Question 10 from 2018. And it's basically about the amount of substance and how you find X, the integer, in a hydrated compound. So a student added 67 milligrams of hydrated sodium carbonate to 200 centimeter cubed of 0.250 mole per decimeter hydrochloric acid in a beaker and stirred the mixture. After the reaction was complete, the resulting solution was transferred to a volumetric flask made up to 250 centimeter cube with deionized water and mixed thoroughly. Several 25 centimeter cube portions of the resulting solution were titrated with 0.150 mole per decimeter aqueous sodium hydroxide. The mean titer was 26.6 of aqueous sodium hydroxide. Calculate the value of X in Na2CO3.X H2O. Show you're working. Give your answer as an integer, 7 marks. Let's get to it. So here we have our hydrated sodium carbonate, and essentially you need to find out X. So once you know the core principles of this, you'll be able to handle all of these questions. You look at the sodium carbonate, the bit before the dot, find out the moles of that. Then look at the water, the H2O, find out the moles of that. Then divide the moles of the water by the moles of the substance before the dot, and you will have X. You round it to the nearest whole number because it has to be an integer. There's a certain amount of water molecules in these hydrated substances that bond around. You can't have 5.5 water molecules. So normally you would heat this hydrated substance to a constant weight. You'd evaporate all the water and then subtract that mass. You'd find out the mass after it reaches a constant weight, and you'd subtract that and you would work out the mass of water and then do mass over MR, which is 18 for water, and you get the moles. That's dead easy. But of course, they did it a really difficult way here. Instead of evaporating the water, they said, well, we have a carbonate. Let's react it with an acid. So the carbonate was reacted with an acid. And the acid in question is hydrochloric acid. And all we need to do is recall from GCSE that acid plus carbonate makes carbon dioxide, water, and a salt. And then we need to write that equation out and work out the ratio between the carbonate and the acid. So we have Na2CO3 plus HCl. You should know this from GCSE, how to do these. So it goes NaCl, which is your sodium chloride, and then we're going to make carbon dioxide and water, or water and carbon dioxide. The order doesn't matter. We now need to balance it up. Well, I've got two hydrogens on the water, so I'm going to need a 2 in front of the HCl. And I've got two sodiums in the carbonate, so I'm going to need a 2 in front of the NaCl. And the main takeaway from this is that my ratio of reaction between the carbonate and the hydrochloric acid is 1 to 2. I'm going to need 2 lots of hydrochloric acid, or moles of hydrochloric acid, for every mole of sodium carbonate. Now, we were also told in the question that we had 627 milligrams of the hydrated carbonate. We need to divide by 1,000, and that gives us 0.627 grams of the whole thing. Now, in order to work out how many moles of sodium carbonate we've got, we need to use excess hydrochloric acid. That's why I've written excess there. And so you kind of need to work out the original moles of hydrochloric acid, and we get the information in the stem, which we'll look at in a second. Then we need to work out the leftover moles of hydrochloric acid, which is how much we react in the second equation, which is our kind of back titration. And then we find out how many are reacted. So let's find out how much hydrochloric acid they added originally, and it was 0.250 mole per decimeter. That's the concentration, and we've got a volume of 200 centimeter cubed. So let's find out the original moles of hydrochloric acid added to the sodium carbonate in this first reaction. And in order to do that, we need to do 200 over 1,000, which is the volume, and multiply it by 0.250, which is the concentration, and C times V gives us N. So 200 over 1,000 times 0.250 gives us 0.05 moles of hydrochloric acid. We know the original moles of HCl that reacted with the sodium carbonate was 0.05. Now we know that some of it was left over because it was excess, and they re-reacted that in a titration with sodium hydroxide. And they took a tenth, 25 out of 250 centimeters of the hydrochloric acid that was left over, and reacted it. And they found that it was neutralized with 26.6 centimeter cubed of 0.150 moles of sodium hydroxide. So what did they actually do? Well, they took the products of the first reaction. That's the sodium chloride, the water, and the carbon dioxide. And of course, they stuck all of that into a flask and made it up to a set volume. Okay, now that contained the leftover HCl. The other products aren't going to react with sodium hydroxide. So they've now done a neutralization, a titration with sodium hydroxide. Now they've reacted it, and of course it forms salt and water. You know that from GCSE. Acid and alkali make salt and water. And we can see from this balanced equation here that it's 1 to 1. So our leftover acid was reacted with that sodium hydroxide in a 1 to 1. So now we do moles over concentration times volume. We know the sodium hydroxide had a 0.150 concentration from the stem of the question we just looked at. And the volume is 26.60 centimeter cubed. We divide by 1,000 to turn it into the correct decimeter volume. And we multiply C and V to get the moles, which is 3.99 times 10 to the minus 3. Now, that is a 1-to-1 reaction, which means we have 3.99 times 10 to the minus 3 moles of hydrochloric acid too. However, that is in 25 centimeter cubed. Remember, we took the 250 and we only titrated 25 centimeters. There was 250 in the flask and we only titrated 25. So to find out how many leftover HCl was originally in that flask, left over from the first reaction, we've got to multiply by 10. And if you do 3.99 times 10 to the minus 3 times 10, we'll find out that in the original 250 centimeter flask, we had 0.099 moles of hydrochloric acid. And that was the leftover moles. So how many were used in the original reaction with sodium carbonate? Well, we take the starting moles of HCl, which was 0.05. We take away the leftover moles, 0.0399. And we find out that the amount of moles that reacted with the sodium carbonate was 0.0101. Now we need to divide that by 2, because remember in the original equation we worked out the ratio of HCl to sodium carbonate was 2 to 1. So we've now found out that we have 5.05 times 10 to the minus 3 moles of sodium carbonate. That's brilliant, but we need our moles of water to finish this equation. And in order to do that, we need to find the mass of sodium carbonate. We can do that by multiplying its MR of 106 by its moles to find the original mass. Why do we need to find its mass when we've already got its moles? Because we need to find the mass of water. So we're going to take 0.627, which is the mass of the sodium carbonate and the water, and we're going to subtract it from the mass of our sodium carbonate, which is 0.5353 grams. And that's going to give us our mass of water. So we go 0.627 minus 0.53 grams, and that is going to give us something along the lines of 0.0917 grams of H2O is what we have. Long way about it, I know. Stick with it. We now need to work out the moles of water. Do you know the MR of water? You've got 2 hydrogens and an oxygen. It's 18. So you divide your mass of water, 0.0917, by 18. We now finally have our moles of water. We have 5.09 times 10 to the minus 3 moles of water. Pretty similar, right, to the moles of sodium carbonate, 5.05 times 10 to the minus 3. We divide our moles of water, 5.09 times 10 to the minus 3, by 5.05 times 10 to the minus 3. Now, you're not going to get exactly 1, but they've told us what is the integer x. They've told us it's a whole number. So the answer must be 1. And there you go. Share with other students, like, subscribe. If you have any questions you'd like me to put a walkthrough to, just hit me up in the comments. Okay, welcome to Let's Get to the Marks. We're looking at 7.8 of the 2023 Paper 1 A-Level Chemistry, and this is on hydrated salts, and it's all about working out the integer x, and it's a big fat question worth 7 marks, 7 whopping marks. So let's get into this one and check it out. Right, let's get this whole question in view. Hydrated aluminium sulfate Al2SO4 3.X H2O is soluble in water. The relative formula mass and value of X can be found from a titration experiment. Aqueous AlH2O6 3 plus ions react to form a stable complex when treated with an excess of EDTA4 minus ions. The excess EDTA4 minus ions is determined by titration with zinc sulfate. The method: dissolve 1.036 grams of aluminium sulfate hydrated in distilled water and make up to 250 centimeters. So straight away, look, we've been given the mass, and that is immediately making me feel like we are going to need our mass over MR times moles. And so we immediately want to note that as we go through. And it says make up to 250 centimeters, then add 25 centimeters from the 250. So what I want to know here is I've gone from 250 centimeters to 25. So I've kind of had a bit of a dilution here, or not really a dilution, but I've taken a portion. It's not really a dilution, but we've taken 25 centimeters of 250. So I just want a little note there, something that's going to trigger me later on to remember that. Of this solution, we're going to add that to 50 centimeters containing EDTA4 minus ions of a concentration of 0.01 mole per decimeter. Now, what have they given me? Mole per decimeter. What does that unit tell you? It tells you you're dealing with concentration. So I want to put on my second triangle here, which is N over C times V, because they're giving me concentration. So now we're starting to get cooking on gas. Determine the excess of EDTA4 minus ions by titrating with zinc sulfate solution in the presence of an indicator. The excess EDTA4 minus ions require 18 centimeters, that's our volume, and 0.0105 mole per decimeters to react completely. Look, I've been given a volume and a concentration, so we've got a great starting place here where we can work out moles. The equations for the reaction are hard. We got 2 equations. We got 1 and 2, so we've got 2 equations going on here. Whenever you get 2 equations in a titration, you're looking at what we call a back titration. And this is where you calculate the excess EDTA and you subtract it from the original volume of EDTA, which we can work out here. And what that does is that allows us to work out how much EDTA reacted in the first equation and work out your missing moles. So let's get into it. We've also been given the MR, which confirms we're going to have to use this equation here. So where do you start in a big dirty 7-mark equation like this? Well, there's a couple of starting points. We've been told we had 50 centimeter cubed of EDTA 4 minus there. So I could actually calculate the original EDTA 4 minus, or I could start down here at the back and work my way up. I tend to start at the bottom and work my way up. If you find these difficult, just start at the bottom and work your way up through the data. So that's why we call them back titrations. So start at the back. So I'm going to work out the excess EDTA 4 minus, and we're going to do that. Let me change the color so it stands out a bit more. We've got volume times concentration equals moles. So I'm going to do 18 divided by 1,000 times the concentration of 0.0105. And this is going to give me my moles, which is 1.89 times 10 to the minus 4. Now, what this has told me, this is the moles of excess EDTA. So I want to label it as well so I know actually what I'm banging on about. So this is excess EDTA. Okay, I'm going to skip the 4 minus for ease. So that's the excess EDTA. If we go down to this equation, we can see that that's in a one-to-one reaction with the zinc. But actually, that was the zinc solution I've worked out. So getting myself in a muddle there. But that does tell me, it doesn't really matter because they're the exact same, but this was the zinc sulfate solution. And they are actually in a one-to-one, as you can see there. So because they're in a one-to-one, that also tells me I have 1.89 times 10 to the minus 4 moles of excess EDTA because they were in a one-to-one. Now I know the excess EDTA. Let's work out the original EDTA by coming up here to the 50 centimeters with 0.01. And then I can subtract the excess from the original to get how much EDTA was used in this first equation. So we're going to do original EDTA was 50 over 1,000. Why am I doing that? Because we need to turn centimeter cubed into decimeters. And I'm going to times that by 0.01, and that is going to give me the original EDTA, which is 5 times 10 to the minus 4, and that is the moles of original. Now I want to find out the reacted EDTA. So reacted EDTA is equal to the original minus the excess. And so I want to do the original, which is 5 times 10 to the minus 4, take away 1.89 times 10 to the minus 4, and that is going to give me my reacted EDTA, which is 3.11 times 10 to the minus 4. So my reacted EDTA, this is how much was used up. So this is EDTA that reacted with Al H2O6, right? So that is how much EDTA reacted over here. Now we can tell that's a one-to-one. So that means I also know now that I had 3.11 times 10 to the minus 4 of Al H2O 6, right? So that's how many moles of that I had. However, we're dealing with aluminium sulfate here. Look, aluminium sulfate. So what I need to know is that this one molecule of this aluminium complex ion only has one aluminium atom in it, whereas there are two aluminium atoms in aluminium sulfate. So if I want to find out how much aluminium sulfate produced this, I need to divide by 2 because, excuse me, these bad boys have 2 aluminiums in them. So these aluminium sulfates have 2 aluminiums. So I need to divide by 2. So let's do that. That's 3.11 times 10 to the minus 4 divided by 2. And that is going to give us 1.55 5 times 10 to the minus 4. So we're going to get, I have 1.55 times 10 to the minus 4, and that is my moles of aluminium sulfate. Now, we've worked our way up to here. Here's where the next problem is. The next problem is that this is in 25 centimeter cubed. That's how many moles of aluminium sulfate I have in 25 centimeter cubed. What I need to do is times that by 10, because we're looking at how many moles of aluminium sulfate were in 250 centimeters cubed. So let's times this by 10. And if I times by 10, we're going to end up with 1.55 times 10 to the minus 3 moles. And that is aluminium sulfate in 250 centimeters. I now want to turn that into grams. Now you might say, why do you want to turn that into grams? What I'm trying to do here, I know the total mass of water in aluminium sulfate was 1.036 grams. So if I can find out how many grams of that is aluminium sulfate, I'll know how many grams I've got of water, and then we can work out the moles of each. So this is my moles of aluminium sulfate, right? God, it's long doing this, and that is scrappy. That's my moles of that. Let's work out my moles of water. So I want to times this by 342.3, because this is the MR of aluminium sulfate. So times 342.3, and we're going to get, I have 0.53 grams of aluminium sulfate. So let's do 1.036. Let's take away the 0.53 grams, and we're going to find out how much of this Al2SO4 3.xH2O is water. So let's do 1.036, take away answer. We're going to find out that we have 0.503 or 504 grams of H2O. So how does this help us work out what X is? If we just look at mass for mass, it's almost a one-to-one in terms of mass, right? Because I've got 0.53 grams of aluminium sulfate and I've got 0.503 grams of water. However, that doesn't tell me what X is, because X, okay, is going to be telling us the ratio of the moles of aluminium sulfate to the moles of water. So I need to compare my moles of aluminium sulfate, which is 1.55 times 10 to the minus 3, to my moles of water. Well, what are my moles of water? Well, I need to take the grams, 0.503 grams, and I need to divide it by the MR of water. Hopefully you can remember the MR of water off by heart. You should know it now. You're doing A level. H is 1, O is 16. So I got two H's and an O. That is 18. So 0.503 grams divided by 18, and we are going to get, we have 0.027 moles of water. Okay, and I got this many moles of aluminium sulfate. So what's the ratio between those? Well, what I'm going to need to do, I'm going to come all the way down to the bottom left because I've run out of room, which is a bummer. And I need to divide the big number by the small number. So 0.027, I've got more moles of water than I have aluminium sulfate, because this is 0.05155 or 1.55 times 10 to the minus 3. And then let's see what that ratio is. So I'm going to go 0.027 divided by 1.55 times 10 to the minus 3. And yeah, and we get roughly 18. So that tells us that there are 18 molecules of water for every molecule of aluminium sulfate. So although the masses were roughly equivalent of aluminium sulfate to water, we had about 0.5 of each. When you convert that into moles, we've got 18 times more moles of water than aluminium sulfate. So X is 18. Like, share, subscribe. Let's get to the marks.
You're still here? It's over.